Crap, I'm not on the first slide, so there it is. Let me get my little picture here. There we go. All right, so it looks like it actually, no, it's still snowing. Okay, so anyway, this is our first little video. This is for our making up of having snow. And I want to get into talking about solutions. I'm breaking this into more digestible pieces, I hope. In this first one, I just want to introduce this to solutions and get some definitions under our belt for how that's going to work. Okay, so solutions are, anything mixed together. Remember, there's a solute and a solvent, and we talked about that in Gen Chem 1. We're going to get it here too. Remember, the solute is present in a smaller amount. I don't know why I don't have these prepped on here. Solute is a smaller amount. Okay, and the solvent is a greater amount. And I know we usually talk about having, well, in Gen Chem 1, we talked about solutions being something dissolved in water, and that's a very common way to do it, and that's a lot of what we're going to focus in on at some point here too. But solutions can really be anything, so that's kind of what I'm getting at here. Like you can have a gas dissolved in a gas, right? This will give you, like, air is a great example of this. You can dissolve a gas in a liquid. That'll give you carbonated water is the best example of this. Soda, that's a gas dissolved in a solution. That's a lot of things dissolved in a solution. Liquid you can do. Solid and liquid is probably the most common thing that we think about. You can even have solid and solid. Any metal alloy will do that for you. And it's kind of really interesting to think about these kind of things. You can even have a liquid solution, and this is like a weird example, but I love it because it's weird. If you take, what is it, potassium, that has 10%, I think, sodium in it. This is a liquid at room temperature, but it's still a solution. Even though you're taking two solids and kind of smushing them together, sodium is really soft, so it's really easy to do that. Most alloys are solids, right? So here we're looking at melted metal. So basically you melt the two metals together and you cool it down and reform it into a new solid that has both things in there. But really, I just kind of want to divorce our brains from thinking about solutions have to be liquids. Solutions can be anything, and they can be anything mixed with anything. Okay. Two big terms. These are new terms I want to get under our belt for us to do here. What? Sorry. Nope, I'm hitting the wrong button. That's my problem. Okay, here we go. Miscible and immiscible. Miscible means that the liquids will mix together, or you say mix in all proportions, okay, where it doesn't really matter how much stuff is there, right? This I think of like alcohol and water, right? It doesn't matter how much alcohol or ethanol or methanol or whatever you put in there, there's always going to be that they completely dissolve each other. And when they completely dissolve each other, they look like one thing, like a pure substance. So that's kind of the idea here. And the miscible thing, it looks like a pure substance. Okay. Things that are immiscible is when the liquids aren't soluble in each other, right? So this is kind of like an insoluble case. We'll talk about soluble and insoluble in a little bit. And kind of a hallmark here is because they're insoluble in each other, the liquids don't mix together. And because liquids don't mix together, they usually form separate layers. So like in this picture, this guy, he's like moving oil and water around. Oil is the yellow on top, and I guess they've dyed the water blue on the bottom. And they don't actually mix together. If you let that sit for a little bit, all the water would sink to the bottom and all the oil would float to the top. We do that a lot in organic chemistry. And hopefully you'll do that with me when we get into it, where we can use this to our advantage and have a very dense organic solvent that's insoluble in water, and you can actually move solutes from one layer to the other, but you can actually see that there's two layers in here with the aqueous water layer on top and the organic layer on the bottom. Okay. That didn't work. Okay. This is And I actually went through and watched this video. This is a really cool thing that he's done, but it's kind of an extreme situation of immiscible. If you're very careful, you can layer these things, and a lot of these things are soluble in each other, right? Maple syrup, corn syrup, milk, that's all going to be soluble in water. But if you're really careful with how you set it up, and because remember, things are going to layer by density, right? So the most dense thing is on the bottom and the least dense thing is on the top. So here we'd say honey is the most dense thing. The lamp oil is the most dense thing. You can see water is dyed green here. It's kind of towards the upper middle. But what's cool is you can get objects to float in the mix based on how dense they are. And it kind of gives you an idea, right? This tomato is more dense than the ping pong ball or whatever these beads are made out of, which are hard to see right here. Okay, there's a soda cap up here that's floating in the alcohol, and a metal bolt has fallen all the way to the bottom. Now they say there's a dye in here. I bet if you watch the video, it's probably easier to see, but it's kind of here, I believe. Anyway, so things kind of sort. I'm trying to make this not too terribly long. This link is on our Blackboard if you want to follow through and read this dude's directions and see the video there. This is another video and I stumbled on this and I like this because it's short and it shows you an actual example. If we were in class, I would do something similar to this. But let's just watch this for a second and see how we do. Yeah, don't do this at home, but you probably don't have hexane at home, so I'm not going to stress about it. Hexane for a reference is I can't write on the video? C6H6, H12, H14, sorry, there it is. And one butanol has an OH group on the end. Remember we talked about OH groups. CH3, CH2, CH2OH with the OH on the end. Butanol's 4, I ran out of room. I still ran out of room. Cool. So that gives us kind of an idea of what we're looking at here. We're not going to do a lot of miscible, immiscible things, but I think these are great terms to throw at us and to make sure we have in there. What I'm going to really want us to be able to do is if we can classify solutions by the type. Okay, and we're going to say type of solution. This is based on how much of solute is dissolved in stuff. Okay, and so we can coin this term here, solubility, and we'll use that a lot this semester. Usually we think about solubility as kind of yes or no. It is soluble or it's insoluble if it doesn't dissolve. But really solubility has a specific definition. It's talking about the max amount of solute that a solution can hold. Okay, the max amount. So at some point, even if it's completely soluble, like if we talk about our always soluble ions, and we'll get back into that too. If we talk about our always soluble ions, you can get even to a limit where those things are not soluble anymore because you have too much in the solution already. Okay, so the max amount is defining what the solubility of something is. Okay, so for example, for sodium chloride, the max amount of sodium chloride is going to be 36 grams of sodium chloride in 100 milliliters of water. Okay, and this I want us to watch out for because this is the unit. I guess technically the unit, I spelled the unit wrong. How weird is, I can't spell anything. Um, this is the unit. Okay, so for 100 milliliters of water, it can hold 36 grams. Okay, this is not milliliters of solution, and we'll talk about that in a bit here. If you're measuring milliliters of solution, you're going to have more solution than you have water because the grams is going to take up some of the space, and because of that, you're going to have more milliliters of solution. Okay, so we can worry about that later on. So the saturated solution contains the max amount. Okay, you can usually tell a saturated solution because you dump a bunch of stuff in there and you stir it really well, and not everything dissolves. You've got stuff left on the bottom here. On the bottom. Okay, that's why I think a saturated solution is the easiest thing to make in the lab, and you'll do this throughout the semester. If you take um, some distilled water and just add solid to it, and just keep adding solid to it until it doesn't dissolve anymore, and as long as you have solid on the bottom, it is a saturated solution. Okay, and as we'll see later, saturated solutions are at equilibrium. Okay, so there's an equilibrium between the undissolved solute and the solution itself, and hopefully we have time in class we can discuss that more. Um, so yeah, the saturated solution contains the max amount of stuff. Okay, so that's an easy to clarify. It contains the max amount of solute. It's going to have leftover solute on the bottom, right? Technically, we can think of in our miscible, immiscible cases, that's a saturated solution because there's going to be a little tiny bit of water that's dissolved in the hexane, and that's a saturated solution because most of the water isn't in there. The most of the water has settled out to the bottom. Okay. The other most common one is an unsaturated solution. We're looking at that over here. And the unsaturated, this is less than the max amount of solute. Okay, so what this means is you can put some solid in there and get it to dissolve, and all of it dissolves. Okay, but there's also none left on the bottom, and it can dissolve more. Okay, so that you can get more things into the solution. Okay. This third type, I want to kind of caution us. This is rare, okay, but it's called supersaturated. And in the supersaturated case, this holds more than the max amount, which sounds dumb. Okay, and really, and then we'll see this later on as well, you can get the solution to dissolve more stuff if you heat it up. Okay, and a lot of this is tricks that cooks and bakers use, especially when making candy, in that you can get sugar to dissolve a lot better when it's hot. And if you cool it carefully, it won't come out of solution. Okay, this is rare. I don't want us thinking that we're going to encounter supersaturated solutions all the time, but they are kind of cool. One of the hallmarks of a supersaturated solution, we're going to remember these guys are rare. They're not very common. They don't happen a lot. Is that if you disturb them at all in just a little bit, right? So here we have a super saturated solution. This person is dripping down, and just the friction of it falling and hitting the surface causes the solute to come out of solution. Okay, and what's coming out of solution is the excess, the stuff that didn't dissolve when that happened. Okay, so interesting. All right, so let's see if we can navigate our way through this question. Okay, we want to figure out what kind of solution is here. What type of solution is formed in these scenarios? So I've got two scenarios for us. It might be helpful for us to remember, that saturated sodium chloride in solution is 36 grams per milliliter. We saw that on the previous slide. Okay, so if we put 30 grams of water in 30 grams of sodium chloride in 100 milliliters of water, that's less than the max amount. So this is unsaturated. Okay, if we put 40 grams in 100 milliliters of water, this is more than the max amount. Okay, now remember we said supersaturated is going to be rare, so I'm not going to call it super. We're going to call this saturated. Okay, And if it's saturated, you're going to have some left over on the bottom. And we want to know, can we figure out how much is left on the bottom? Okay, let's think this through. Remember, saturated means the max amount. So our max amount is 36 grams, and we put in 40 grams. Okay, hopefully your brain's getting there faster than I'm saying it. But that means if we have 40 grams in there, we can hold 36 grams. And that means we have 4 grams on the bottom, because that's the difference when we do that. So you should be able to see it on the bottom of the solution. Okay. That's what I've got for this. I hope this is okay. I will see you again in class and hope you're staying warm.